All right. Hi, everyone. Thank you for joining our talk today. So today we're gonna revisit this, really good old Russian proverb, trust but verify, by uncovering the hidden risk of inaccurate SBOM with JBomAudit, which is a tool we developed along the way. So I'm Dhilung Kirat, and my colleague, Yue Xiao. So we are from IBM Research, security researchers, and we have been working on software supply chain security and its issues for the last couple of years. And the notion of this, trust but verify comes up very often, right? In fact, in this very forum, 2 years ago, I believe, we presented Code Genome, which is about extracting fingerprints, semantically meaningful fingerprints from the code. And that is directly inspired by the idea of trust but verify. But why do we need to follow this trust but verify security principle? This is because of the semantic gap. And you ask, what is the semantic gap, right? This is basically the potential gap between the semantics conveyed by the metadata, a label, and the actual content of any distribution. Let's say, take an example, right? So let's say you want to get a jar of paint. Usually it comes with some metadata, like the label, like the brand, maybe the color, what is the color, obviously, and maybe some certificates. And you may trust that because it's coming from some reputable brand. But what really matters is that what is the actual color of the paint itself, not the metadata. And when you don't blindly trust the metadata, when you use it, the color, you actually verify it by looking at it, right? And sometimes there might be some semantic gap, like maybe the color name was vague. Maybe it's like a space gray or a midnight blue. But when you look at the color, it's very easy to verify the semantic gap. But let's take another example, another kind of jar, which is a software jar file, very common distribution format for Java software. And it also comes with metadata, like the name of the package, POM file, or SBOMs. And again, you might trust that, right? Because you trust the vendor. Maybe the metadata was signed and signature checks out. But again, what really matters is the actual code that comes with the package, not the metadata. And we shouldn't blindly trust the metadata, but verify it. In case of the paint, it was easy, you just look at it. But when it comes to software, it's not that easy, right? Unless you are Neo from the Matrix, just by looking at the code, you cannot determine whether the metadata aligns with the actual code. And this actually, in fact, stems from the fundamental limitation that it illustrated by the undecidability of the halting problem. And the halting problem is basically deciding whether a program will stop or halt or run continuously when it's executed. And the theory states that there can be no such tool, no such program, or no such algorithm that can tell exactly, reliably, the halting behavior of any possible code. And day-to-day, the software that we use are written in Turing complete language. So that means the problem or the challenge or the decision problem of whether the metadata aligns with the actual code can be reduced to halting problem, which is proven to be undecidable. And what this means is that resolving the semantic gap is a very complex and hard problem, right, compared to the physical object that we saw on the other side. So what can we do about it? So mostly you resort to some heuristics, look into some common cases, easy cases, and that's what the approach that we have taken for this. And also you can focus on a certain portion of the metadata or SBOM and try to verify just that. And one of the key information in the SBOM is the dependencies, right? Components, how they are dependent. And this talk will be focused on that. So let's look into an example of SBOM, software bill of material. So this is one example, which is like Cyclone DX format. And there are many different kinds of information there, but today we're going to focus on two kinds, the components and the dependencies. The list of components basically lists all the different components that are related to this package, and the dependency tells us how they are related. And if you think of the dependency graph, the components are nodes and dependencies are edges, right? And if you look into some of the items in the components, it lists the name of the package, the versions, even PURL. And because of that, one of the key use of SBOM has been in the vulnerability management. So there are many tools that takes this SBOM and then directly cross-reference with their vulnerability database, and they can figure it out if there are any problem with the SBOM and the package that comes with it. So back in 2021, there was a White House executive order related to SBOM, and the idea is great, right? So if every software comes with something like this, the SBOM, the organization can use it to automate many of their vulnerability management, since it also includes licenses, so you can deal with compliances and also protect your software chain, supply chain. But it only works if the software SBOM is complete and accurate. So as a follow-up, NTIA come up with established this SBOM compliance rules, and one of them states that as SBOMs, an SBOM should contain all primary, which is the top level, components, along with all their transitive dependencies, which is the second level. But as you can guess, it's not always the case. So one example you can take, this is one of the open source project. So if you look at the code, it's dynamically loading some classes, right? But if you look at the SBOM, it's completely missing there. Another different kind of, the inconsistency is the missing transitive dependency. For example, here, so there is a Parquet pig file, the jar file, that depends on some class that needs to be get from the SL4J. And in turn, the second jar file depends on another class that comes from log4j. But if you look at the SBOM that from the original Parquet pig file, that's completely missing. The log4j is completely missing. And as you might have guessed, if you depend your vulnerability analysis completely using just the SBOM, you're going to miss that log4j is there in the package. And if you check the vulnerability database, obviously it comes with many, for this particular version, of course, direct vulnerability, some of them ranging 9.8 in CVSS score. Another kind of inconsistency is the incorrect dependency. So there is a SBOM, it says, hey, this package depends on this another module or package, and you might go ahead and check the vulnerability, and there's a vulnerability. Oh, so this package must be vulnerable. But turns out this is an incorrect dependency, and that just introduces false positive. You spend time and all that, right? There are many implications of inaccurate SBOMs. Originally, it's designed to give you transparency of the software component and all that, but it can be the source of confusion and harm. As we discussed, you can undermine the effectiveness of the vulnerability management, mislead the analyst, or waste time. In some cases, when there's a missing dependency, it can even leave critical vulnerability overlooked. So all this is happening, again, going back to the problem of the semantic gap. So there is the SBOM, which is the metadata that doesn't match with the actual code. And as a team, we have been fighting this semantic gap for a while, almost more than a decade now. Some of the early work, going back to our graduate school days, some of the early works were focused on n-gram instruction, code instruction and n-gram, and trying to make sense of what the code is. So Sigma, for example, that's something I worked on, was actually taking the entire binary and applying some signal processing and fuzzy hashing approach to make sense of the code. The Malgene, also something I worked on, that actually looked into the dynamic behavior of the binary, of the executable, not the static part, and trying to extract malicious gene in this case, because I was trying to detect malware. But the problem is very generic, right? So you have software or a program, and you're trying to extract what it means. So fast forward to 2021, everybody knows there was a huge problem with the log4j, Everybody is scrambling, trying to find some scanner to detect, whether they have some vulnerability lurking around. So we also went around, and many of the tools, I would say that almost all of the tools were using the metadata, the POM file, to detect, whether the log4j is there or not. So that would not cut it, right? So it was missing many of the existing vulnerability because it was not looking at the code. So we started writing our own scanner to find, log4j buried on legacy components and systems, right? And that actually is one of the precursor of what we're presenting today. So all these different approaches and ideas we combined and created a code genome framework that is now open source. As I mentioned earlier, 2 years ago we presented here. That allows us to extract semantically meaningful fingerprints from code. And last year at Black Hat, we actually demonstrated using this framework to automatically detect some of the very complex supply chain attacks, such as XG backdoor, which is very stealthy and happens at the build time. So again, following this thread of fighting with the semantic gap, today we're going to present JBomAudit, which is specifically focused on Java code and trying to make sense of it, and specifically focusing on the dependencies. And for the technical detail and all that, I would hand over to my colleague, Yue.
Thanks, Dhilung, for the introduction. Hello. Can you hear me? It's good? So in this work, we mainly focus on analyzing the SBOM in the Java domain. And specifically, we collect more than 25,000 SBOM and JARs from the June 23 and to the April 24. And in this study, we proposed a formalized consistent model that identified different types of inconsistencies between the SBOM and the jar file. In order to detect those inconsistencies, like detect the missing or incorrect dependency, we developed an end-to-end tool called JBomAudit, which automatically evaluates the correctness and the completeness of the SBOM. Additionally, we also performed a comprehensive large-scale measurement study on the SBOM non-compliance. We also investigated their root cause and also analyzed their security implications. We identified two general categories of dependency issues causing non-compliance: missing dependencies and incorrect dependencies. Each of them pose distinct security implications. So missing dependencies are those components that used in the distributed code, but in the SBOM, they are failed to disclose those dependencies. So you can imagine if a missing dependency has a vulnerability, it won't be tracked by the vulnerability scanner built on top of SBOM because these dependencies are actually not listed in the SBOM. This means that security team may never patch it and leaving the software exposed to attacks. The missing dependencies are further can categorize into different types, like missing direct dependency, missing transitive dependency, missing transitive relationship. The incorrect dependencies are those dependencies listed in the SBOM, but actually are not used anywhere in the distributed code. When a SBOM lists an incorrect dependency, that means that security team may waste the time to investigate and fix the issues that don't exist. So this not only wasted the maintenance time, but it also distracted the security team from the real threats and eventually will potentially delay the critical security fix. And again, the incorrect dependency can also categorize into these three types: incorrect direct dependency, incorrect transitive dependency, and incorrect transitive relationship. So to detect those types of inconsistency, we developed an end-to-end detection tool. So let's take a deeper look at this end-to-end tool called JBomAudit. The design of this tool includes three major components: data collection, dependency tree extraction, and a compliance check. Particularly in the data collection component, as we said, we download all the artifacts hosted in the Maven platform, and in the end, we collect more than 25,000 SBOM and its corresponding jar files as our data set to perform the measurement study. And after that, we extract the dependency tree directly from the jar files using a binary analysis tool called jar PKG tags, which I will illustrate later. And additionally, we also parse the corresponding SBOM to extract the claimed dependency tree. And in the final analysis, we will perform a comparative evaluation between these two dependency trees and output any inconsistencies between them. So let's take a deep look at the JPKG tags. So basically, it scans the bytecode to identify the reference that indicate the use of Java class in the distributed code. Specifically, it analyzing the Java bytecode to capture like the reference from the external classes, method parameters, annotations, or even the dynamic features. After retrieving the utilized class, our next goal is to identify the dependency that actually provide those files. So we first need to get the package name by removing the last label separated by dot from the utilized class name. And then we get the external dependency that provided this package name by querying a comprehensive Maven database. And finally, we will iterative to construct the dependencies tree. And eventually, we will get the dependency tree from the jar file and as an input of our comparison tool. This table shows the overall result of the non-compliant SBOM detected by our tool. Specifically, in the M1 type, it is missing direct dependency. As we can see, we detect almost 8,000 SBOM that failed to include the direct dependency. And it's average 6 dependency missing per SBOM. And for the incorrect, M1 is the incorrect direct dependency. We detect roughly close to 20,000 SBOM that inaccurately report an average of like 4 dependencies. So the errors in those direct dependency, either missing or incorrect, are especially concerning because they make SBOM less reliable and also can disrupt the tools that relied on them. For other types of dependency like M2, M3, N2, N3, they are all incorrect or missing transitive dependencies. As you can see the number here, they are huge. So we uncovered numerous inaccuracies with the transitive dependencies. Since this issue is so common and it is crucial to have the strict compliance checks and quality audits to ensure that SBOM are actually accurate and useful. And this figure highlights the top 15 missing dependencies in the SBOM. As we can see here, the Google Guava is the most frequently omitted direct dependencies. And what concerning is that every version released before June 2023 contains at least 1 known vulnerabilities. So if it left undisclosed, those vulnerabilities can go undetected by the vulnerability scanner, and it will pose the severe security risks. And this figure shows the top 15 incorrect listed dependencies. Those dependencies are commonly associated with a category like annotation libraries, logging framework, or the utilities tools. We also analyze the security implications of those missing and incorrect dependency by examining their impacts for the vulnerability management, because a lot of vulnerability management tools are built on top of SBOM. So the missing or incorrect dependency will definitely impact the performance of those tools. So here we use a bubble chart to illustrate the severity distributions of the vulnerability associated with the non-compliant dependency and their impact on SBOM. So in this chart, each bubble will represent our vulnerability. And the y-axis shows the CVSS severity score, and the x-axis indicates the number of unique non-compliant dependencies linked to each CVE. The size of this bubble reflects the number of the unique non-compliant SBOM that are affected by those vulnerabilities. As shown in this figure, a significant majority of those vulnerabilities are rated as a high or critical. This kind of distributions underscore that the security risk posed by the non-compliant dependencies. And a notable example is here, this CVE. It clarified as a high severity, which influenced 41 dependencies in our dataset, and also exposed more than 2,000 SBOM to potential security breaches. So the SBOM are supposed to help us improve the software transparency, track the dependency for the security and compliance, identify and fix the vulnerability efficiency, but the reality is many SBOM fail to meet those goals, and dependencies are often missing and incorrect. And the security tools relied on those SBOM or may overlook the real threats or waste too much time on the non-existent vulnerabilities. So you may want to ask, why do SBOM released by the developers often misreport the dependencies? So in the next few slides, we will break down the root cause behind those issues. So one of the biggest root cause is the insufficient design in the SBOM generators. So in our data set, 99% of those SBOM are generated using third-party tools like CycloneDex Maven plugin or CycloneDex Gradle plugin. While those tools are widely used, they have the key limitations. They rely solely on a single metadata POM file to generate the SBOM. This metadata-based method works fine for the simple project, but it fails in the more comprehensive setup where the dependencies are declared across multiple files. Examples including like the OSGI-based projects, which use additional OSGI manifest to maintain the dependencies. And also like some Eclipse project, they may list the dependency just using class paths instead of using the build files. And also some customer configurations or additional dependency sources can get completely ignored by current SBOM generators. Since most of the SBOM generators just rely on one single metadata to create SBOM, the problem even gets worse is that the metadata file itself is incomplete or inaccurate. So why this will happen? Because the metadata files like the POM file are usually manually maintained by the developer, and the human make mistakes. To understand how much this affects the SBOM accuracy, we also check whether the missing or incorrect dependency in SBOM will also represented in their POM file. And in our study, we found that 77.25% of missing dependency in the SBOM were also absent from the POM file. And 85% of the incorrect dependency were also wrongly listed in the POM file. So the strong correlation underscores that the significant impact of the incorrect metadata on SBOM generation, and highlight that the importance of the careful maintenance of those metadata files to ensure its correctness. And another root cause is the improper usage of the SBOM generators. Typically, developers are expected to configure those tools like Cyclone Maven plugin in their main POM file that governs the entire project. But in our study, we found that there is some instance where the developer mistakenly configured the SBOM tools in the submodule rather than in the main project file. So this will result SBOM that only reflect the dependency of that submodule will also, of course, it will omitting others and leading to the incomplete SBOM. Last major challenge with SBOM generation is inconsistent interpretations of what should be included. So different developers may have different views on which dependency should be listed on the SBOM, leading to the unnecessary or incorrect entries. So in our study, we found cases where the developer included the provided and tested scope dependency in the SBOM, even though those dependencies are not actually in the final distributed job. So in our study, we believe that the provided or tested dependency are not belong to the production phase SBOM because they are not part of the final software or package. Including those kind of dependency will cause noisy and make the SBOM misleading and even hard to use. So here the key takeaway is that for SBOM to be truly useful, developers need clear guidance or the educations on what should and what should not be included, and ensuring that only relevant dependencies make it into the final SBOM, not including some noises in the SBOM. Okay, then in the next few slides, I will show our demo of our tool. And before I show the demo, I will introduce two scan mode supported by JBomAudit. So JBomAudit supports two comparison mode for the missing dependency detection, controlling the granularity and the position. So the first is a layer-based comparison. So it performs the layer-sensitive validation, ensure that dependencies are disclosed at the correct hierarchy in the SBOM. As shown in this figure, as we can see, the dependency labeled in the purple color are the transitive dependency listed in the SBOM. But after we analyzing the jar file, we found that these two dependencies are directly used by the target jar file. So here our tool will flag two missing direct dependencies. So this mode will help us identify cases where dependency layers are mismatched. And another mode is global mode. It performs a more strict validation by checking the entire SBOM dependency tree. As we can see here, the two transitive dependency are listed in the SBOM. They are directly referenced in the dependency tree we extracted from the jar file. So here we will not flag the missing dependency. So now let's walk through a quick demo of how JBomAudit can detect missing or incorrect dependency. Okay, let's start by clone the repository, and then we create a virtual environment, and then we install all the necessary dependencies. Next we will need to prepare the target BOM file and the jar file. Here we create a folder specifically following the Maven naming convention, like group ID, artifact ID, version ID as a project folder. And next we will pull down the SBOM from the Maven central repository as long as its jar file. And these two files will serve as the input of our tools to do the actual comparison. Now let's get back to the main folder. And now currently we are running the analyze tool in the global mode. So it will first download all the dependencies listed in the SBOM for the following validation. And it may take some time, depends on the size of dependency listed in the SBOM. And once it's complete, then our tool will analyzing the two dependencies and two dependency tree and output a summarized table which shows the non-compliance type and associated dependencies. And as we can see here, our tool flagged 3 incorrect dependencies. You can also go to the result folder to take a deeper look at the result. Here we have the compliance result.json, which lists various different types of non-compliance and also cross-check whether the packages are referenced in the code or not. And now we can go back to the main folder. We can take a look at the layer mode comparison. Yeah, here is the layer mode comparison. As we can see here, we detect 5 missing direct dependency because we perform the layer sensitive comparison. And again, you can go to the result folder to take a deeper look at the result. As we can see here, it lists which package is being used in which binary file, which give you more visibility of the root cause of why there is a missing dependency. Yeah, this is pretty much of the demo. And the key takeaway here is that to ensure the SBOM is correct and comprehensive, we should inspect the code directly rather than relying on the potential unreliable software metadata. And it is crucial to make sure that SBOM are correct and comprehensive to mitigate the supply chain attacks. We also open source our tool, JBomAudit, and feel free to check it out. And our study demonstrated that currently in current state, a lot of SBOM in the Java domain are not correct. You trust, but you should verify. Okay, that's all about our talk, and welcome to any questions.
Test. There we go. It seems like you just built a better SBOM generation tool for Java. Like your analysis identifies the differences, but couldn't it also be used to generate a proper SBOM for the jar in question?
Yes, we can, because we have a binary scanner tool like jar PKG tags, which will unpack the jar files and dig deeper into the code itself to extract all the reference and then find out which external dependency provided those external package name. And we can, of course, generate SBOM. Then that SBOM would purely based on the code base. Yeah.
Yes, to add to that, the parent project, the code genome, this is the sister project, right? So the code genome actually, one of the demonstrations was exactly that. You give me unknown binary. I know nothing about, you know nothing about it, and then we scan it, look at the code, and then find out like this piece of chunk coming from this module, this from this module, and then actually generate a complete SBOM. And this is exactly, you're right. So this tool can generate more accurate SBOM. That's how actually we're verifying it. It just, at the moment, the code doesn't support generating an SBOM as like Cyclone DX or anything like that. But I think it should be actually quite easy. And since it's open source, somebody can contribute, and yeah, that'd be nice.
I do have a second question. I was going to let someone else talk, but
Sure.
So for less structured languages, how might you approach this? So a language where you don't have quite such a strict class inheritance model where you can very clearly tie the import of a class to a particular jar file that then could be downloaded and pulled in. So I come from JavaScript land. I can't, it would be difficult in JavaScript to identify everything if it wasn't in the manifest.
Yeah, exactly. So that's the problem with a semantic gap, right? So it can be very convoluted code. You cannot guarantee. So you always look for some heuristics, and you try to cover everything, but you cannot guarantee that. So one of the approaches with the code genome, the main project was actually looking at the code not just for the imports like the dependency, but actually the actual code itself. and then extracting what I was saying, the semantic fingerprint, meaning if you have a function, it is actually works on the function level. So if there's a function that does something like maybe do some complicated, computes a MD5 hash, for example, right? And that code, so if you have functional equivalence that is coming from some other code that this code is actually what it does, and that's how it's pulling it, the information. And sometimes you don't even care who is writing the code if you can guarantee that this code exactly does this, right? So that's the idea we're going through, because you can guess like MD5 implementation might be coming from so many different libraries. So there's also the concept of what they call it, in the language, like what they call I forgot the terminology, the accent, it's doing the same thing but slightly different. So what we try to do is reduce to the minimum set. We're using LLVM to reduce the optimization levels and doing canonicalization so that it only extracts what the computation is. And if you go into that raw level and then compare, then you can pull, even if it's unstructured language. In case of Java, sorry, you said JavaScript, right? You still need to compile to its VM, right? And you directly look into that. What does it compile to? And that bytecode you can compare and then tell what it's doing. But probably you have to do it in the memory, which can be quite tricky because you can dynamically load things and pull other scripts in it as well. Yeah.
So if that's the case, you said you're gonna do it at the VM layer. So how are you gonna deal with the code that directly compiles to native code? Like in C, I could have it listed in my makefile I dynamically link to it, or I could just do their open at runtime, right? So how do you envision that to be solved?
So that's a great question. So you were asking, if I understood correctly, so if it's dynamically loading some code, then how do you identify whether that is linked or not, right? Is that
right? And also, it's like native code. It's not like there's a VM layer you could use.
Oh, the VM layer is. I'm just alluding to the fact that for JavaScript you have to do that. But if you're talking about the Linux or the C program, then you still have the binary you compile to, and then you can look at the binary and you exactly know what it's doing, more or less. I mean, with the fact that there's still the semantic gap and all the undecidability is in play. But so once you look at it, at least statically you can tell what are the functions that you statically compiled. So that's something we can guarantee. But the dynamic is something that's in next level, right? You can probably do that as I was alluding to. So you need to get access to the memory, and you still need to keep scanning what is happening. And there's a whole other area, because my background is malware analysis, that self-modifying code, for example. That's completely different ground, right? So how do you even do that? And there could be hundreds of layers of encryption. So that's where what I was alluding to, the fact that it's undecidable, right? So you cannot, it's a halting problem that we're trying to solve. But generally, if it's not malicious, usually these are a simple problem, and that's how you would approach it. Yeah.
All right. Thank you.
All right. I guess if there is no question, that is it. Thank you. Thank you for
coming. Yeah.